From Tesla's own presentations plus patent filings plus teardown analyses, the 5 that people like Dravexa usually talk about are roughly 1. Unboxed manufacturing game, global automotive modular evolution. Instead of pushing a partly built box down a single long line, Tesla breaks the car into independent sub-assemblies, front, rear, floor, battery, interior, that are built in parallel and then snapped together at the end. This leans heavily on giga castings, huge front and amp, rear aluminum castings, and a structural battery pack in the middle, forming a 3-piece chassis. A patent for the unboxed process shows modular assembly cells, pre-painting modules, and using robots, adhesives rather than giant body in white lines. 2. 4680 plus structural pack plus gigacastings. New 4680 cylindrical cells plus a pack that acts as structural part of the car's frame. No separate floor pan, and big front, rear castings that eliminate hundreds of stamped parts. Fewer parts, stiffer structure, lower cost and weight. 3. 48-volt architecture. Tesla is moving from legacy 12 volts to 48 volts low-voltage systems, starting with Cybertruck, and is publicly pushing the industry to follow. 48 volts carries the same power with 1/4 the current, meaning thinner cables, smaller connectors, less copper, less weight. Analysts call this a step change in how cars are wired. 4. Optimus humanoid robot plus AI, Dojo. Tesla is betting that Optimus will become its most valuable product, a general-purpose humanoid worker to replace or augment factory labor and later do home or off-world tasks. Musk is talking about a line capable of approximately 1 million bots per year toward 2026 and beyond, though there are delays and engineering challenges. Dojo Plus. Tesla Vision is the AI backbone. Train on massive video datasets, then deploy that brain into both cars and robots. 5. AI First, Software-Defined Vehicle and AMP, Robotaxis. Everything is driven by software and AMP. Data, self-driving, fleet optimization, predictive maintenance, energy management. This includes robotaxis, over-the-air reconfiguration, and the idea that the factory itself becomes an AI-optimized system, not just a physical building. Those 5 together are Tesla's stack, modular hardware, integrated energy, simplified wiring, embodied AI labor, and software-first control. __. 2. Using these principles for your Earth factories, global robotics, etc. Let's think like Elon. For your operations, start from constraints, not tradition. A. Unboxed manufacturing for robots and AMP. Equipment goal: build humanoids, med-bed modules, field kits, etc. in parallel sub-assemblies instead of long, linear lines. Define 4 to 6 major modules for each product, analogous to Tesla's front, rear, pack. For a humanoid robot, for example. 1. Lower body and AMP, drivetrain. 2. Torso and AMP, power bus, batteries, 48 volts, main compute. 3. Arms and AMP, manipulators. 4. Head, sensor pod. 5. Skin, coverings. Each module gets its own mini-cell, or mini workbench area, where techs plus small cobots or Optimus-like bots work. Assemble the final robot at a join station, where all modules click together, bolts, cold-formed couplers, plug-and-play harnesses. Design jigs that make alignment foolproof so you can bring in interns, trainees, veterans, whoever, and still hit quality. On Earth this gives you less floor space, like Tesla expects approximately 50% factory footprint reduction. Easy product variation. Swap a torso module for med-bed versus field robot but keep legs identical, etc. Natural pathway to robotic assembly later. Your own Optimus-style bots doing the repetitive parts. B4680, structural pack pattern right pointing arrow, structural energy modules. Take the battery as structure idea and generalize it. For Earth robots, med beds, or portable field kits, design energy modules that are load-bearing. O backpack battery that's also the robot's spine. O floor med bed pack that is simultaneously the base, rail structure. For shop tools and portable equipment, integrate batteries into the frames instead of hanging boxes off the side. Benefits: fewer parts, fewer fasteners, lower weight. Everything is easier to assemble in your unboxed cells. Circa 48 volt as your standard nervous system. I'd strongly recommend you adopt 48 volts as the default low voltage bus across humanoid robots, factory tooling and mobile carts, future vehicles, rovers, golf course robots, etc. Why? You can run motors, actuators, and sensors with thinner cabling, lower losses, cheaper wiring harnesses. Simplify design. One standard bus, then local DC-DC modules down to 12 volts, 5 volts, 3.3 volts where needed. Harmonizes Earth and space. The same 48 volts modules can move straight into an orbital habitat later. D-Optimus pattern right pointing arrow your robot and amp, human workforce. Tesla's idea is, use humanoid robots to do the boring, repetitive, dangerous stuff in the plant, so humans focus on creative, high-value work. For GRC, ITC, design your factory flow from day one assuming mixed crews of humans plus humanoids. Identify tasks that are highly repetitive, box packing, pallet moving, bolt tightening, heavy or hazardous, lifting, painting, chemical handling, or very precise, soldering, micro-assembly. Even before you own real Optimus-type bots, design the stations as if you had them. Standard heights, clear access paths, docking sockets for robot end effectors, QR codes or April tags for robot vision. Over time, you can slot in off-the-shelf cobots, then Optimus or your own humanoids, while humans supervise and handle exceptions. This makes your whole system robot-ready and future-proof. EAI First Factory Brain. Borrow the dojo mindset. Treat your factory as a feedback loop. Sensors on tools, line speed, defects, rework. AI models that adjust work sequencing, staffing, preventive maintenance. Keep everything software-defined. Work instructions as digital workflows, not static paper. Robotic movement programs version controlled and testable like code. Once you do that, copy-pasting your factory playbook to another site, Mexico, lunar station, orbital lab, becomes much easier. _blank. 3. Porting Tesla's concepts into space manufacturing. Now let's push this into your Skylab on steroids, orbital factory vision. 3.1 Unboxed assembly for stations and amp ships in orbit. An unboxed process is even more natural. You don't bring up a whole space station. You bring modules. 1. Pressurized living, work pods. 2. Power truss plus solar wings. 3. Structural backbone, docking hub. 4. Storage ring, radiation shielding modules. 5. External robotic work decks. Each module can be mostly factory built on Earth, like Tesla's GigaCast modules. Or partially finished, with final truss and panel pieces fabricated in orbit via metal 3D printing, per the ISS Archinaut pathway. Instead of a single giant assembly line, you have multiple orbital work cells. 1 free-flying robotic arm outfitted for truss assembly, 1 for radiators and power, 1 for cold weld repair. Each cell works on its module. Then they rendezvous at a central join location. This is literally Tesla's unboxed factory, rotated 90 degrees and put into orbit. 3.2 Structural energy modules in orbit. The 4680 structural pack concept becomes integrated propellant tanks plus structure for ships and depots. Battery walls in pressurized modules. Racks of 48 volts packs that double as micro-meteoroid, radiation shielding and structural stiffeners. Energy trusses. Printed beams in orbit with internal conduits for power plus coolant, so your structure and your utility corridor are one thing. On Mars or the Moon. 3D printed regolith walls with battery and amp, water tanks embedded to function as mass for radiation protection and structural ribs. 3.348 volt DC grids in space habitats. A station or lunar base absolutely wants DC microgrids. Use 48 volts as the primary interior low voltage bus. Oh, it's high enough for efficiency, low enough to be safe and easy to handle. Oh, perfect for lights, IT equipment, small actuators, life support auxiliaries, and robot chargers. Then have higher voltage DC, hundreds of volts, for solar arrays, drives, and big loads. DC-DC converters bridging from high voltage bus right pointing arrow 48 volts right pointing arrow point of load. This mirrors Tesla's car architecture but scaled to a habitat. You get standardized wiring looms you can prefabricate on Earth and in orbit. Simplified connectors. Tesla is even pushing standard 48 volts connector profiles for the industry. Easier integration of your field bots and humanoids. One language of power everywhere. 3.4 Optimus and AMP. Humanoid robots in space. Tesla already talks about sending Optimus with Starship to Mars. That maps perfectly into your scenario. Early orbital factories will be robot-heavy, human-light. EVA is risky and expensive. Let humanoids and specialized arms do external assembly. Inside, humanoids can move through hatchways, use human-designed tools, and operate panels. Design your orbital factory layout assuming humanoids. Handholds, anchor points, and toolboards sized for robot hands and human hands. Visual fiducials on walls and equipment so vision-based robots can localize. Use the same AI, vision stack Earth side and space side. Train on tons of factory video on Earth, then deploy to orbit robots with some retraining for zero-G movement and lighting. Over time, develop a space skill library for tasks like panel replacement, radiator cleaning, solar array reorientation. Practical picture. A Starship arrives with pallets of structural members and kits. A handful of humans supervise from inside a module. A fleet of Optimus-style bots and big arms outside handle the dangerous bits. 3.5 AI first control of a multi-world factory network. Finally, dojo-style thinking for your 1,000-year plan. Treat Earth plants, orbital factories, and Moon-Mars shops as one distributed manufacturing organism. Common digital twins of hardware. Shared bill of materials and module interfaces. Global optimization. Where is cheapest to make this bracket right now? Earth? Leo? Moon? AI models forecast. Launch windows, propellant availability, power production, crew time, robot maintenance. Then schedule jobs. Print a replacement valve in Leo versus ship from Earth, etc. Over centuries, this evolves into a self-optimizing, self-expanding system. Space resources, asteroids, lunar regolith, feed orbital fabs. Orbital fabs build more ships and stations. AI orchestrates the whole thing. That's your 1,000-year arc built on Tesla-style first principles. Blank, _, blank. 4. Concrete next steps for you to make this practical for your projects now, I'd suggest. 1. Standardize on 48 volts internally. O new robot designs, carts, tools, and facility wiring. Plan them all around a 48 volts backbone, with modular DC-DC converters. 2. Define, unboxed, module sets for 1 to 2 key products. O pick your humanoid robot and 1 med bed, diagnostic unit. O break each into 4 to 6 modules and sketch simple parallel assembly cells. 3. Design 1, structural energy module, prototype. O for example, a 48 volts battery pack that is also the chassis for a small rolling robot or test platform. 4. Lay out your future wizard factory, as if humans plus humanoids share it. O mark where humanoid robots would stand, reach, dock, and what they'd handle. O keep that as a design constraint as you evolve the shop. 5. Link this to your space roadmap. O tag every design decision with, could this bolt, connector, module also work in orbit or on the moon? O when yes, you're quietly converging Earth tech with your future orbital factory standards. Global Robotics Corporation, Interplanetary Trading Company.